Quadratic applications. I'm going to give you just kind of 3 applications. There are many applications, and in school and maybe in life, you're going to run into numerous things that might be dealing with this. But at least I hope I give you some kind of a sense where you can apply these quadratics and then how to solve some, I guess, relatively interesting problems. Now, this first example is given that the perimeter of a rectangle is restricted to 40 meters. Find the values of the length and the width that would maximize the surface area of the rectangle. This problem was actually something that I did, and it was related to grade 9 videos. I'm going to put up a link up above to exactly the same problem, except in there I only utilized really just graphing, and I didn't talk about quadratics at all. But you'll notice that this is really just a quadratic problem. And now with the tools of quadratics that you have, you can actually apply it without graphing whatsoever. All right, so maximizing the surface area. We want to be able to maximize what this is. And the only thing that we know is we know what the perimeter is. The perimeter here is 40 meters. Now, it could be anything. It doesn't have to be 40. You can restrict it to anything that you like or whatever it might be within your problem. So if that is 40 and I want to be able to maximize A, so how can I solve this problem in general? Because the maximization of the area is really width times length. So I have 3 unknowns. I have A, which is unknown, W, which is unknown, and then L, which is unknown. And the first thing that I do is in this problem is, well, I just want to really just have kind of 2 unknowns, because if I want to match it up to a quadratic, then I want to have a relationship. So in this case, it would be a relationship between A and then between another variable. It's kind of like y is equal to, ax squared plus bx plus c. I want to kind of have it in that format. And what I'll do is first is I'm going to take this equation, because I know what the perimeter is, and I will isolate it. So you can isolate it either for W or for L. So doesn't really matter. And then what I'm going to do is, once I isolate, I'm going to substitute it back into this equation. And it's going to get rid of one of the variables. So let's do that. So I have 40, which is equal to 2W plus 2L. Let's just, for the sake of this, so I'll isolate for the width. And now if I'm going to be isolating, so I'll bring over the negative 2L, so over on this side, so that because it changes sign. And then I'm going to divide by 2 on both sides, and it's going to give me what the W is. Now, so this is 40 divided by 2L, and this whole thing is divided by 2. Now, 2 actually goes into 40, and it goes into 2 as well. So here, in terms of simplification, this is going to be 20 minus L. That's what I have within there. And again, because it comes from the perimeter, it kind of makes sense that it's 20 minus L for that. Now, once I have this, I'm going to take this W and I'm going to substitute it into this equation. Why am I doing that? Is because I don't want to have W times L, because those are 2 variables that I don't know. And I want to be able to maximize this area. All right, so that's what I want to be able to do. Now, remember, in quadratics, maximizing means that we will have, if we would graph it, we would have some kind of a parabola. Okay, so that would be looking like this. And if that parabola looks like that, then we have a maximum point. All right, okay, which would be the kind of the peak, or in our case, it's just the vertex. So let's see if that happens. So now I have A is equal to, I'm substituting, so 20 minus L, and then L right here. So this is what I have. So that's substituted back in here. Now notice, this now is basically a quadratic problem. Now why is it a quadratic problem? This is actually in factored form. And the factors are 20 minus L and then L, right? So those are my factors that I have, and I'm trying to maximize A. And from here, you don't have to really do anything else, because, okay, so what I have is I have my 2 zeros, okay, so I have this is a 0, and then this is a 0. And notice that if I would distribute the L inside, I would have 20L minus L squared, which indeed is quadratic, right? So that would have been a quadratic problem. Now with this, so if I want to be able now to see and maximize my surface area, and then I want to be able to find this peak. So I'm going to be trying to find what the vertex is. Now recall, so this A that I have right here, so this is like your y is equal to, this is 20, minus x times x. You can think of it this way. And if you think of it this way, then it's much easier to think of the quadratics. So from the factors, so these I'm going to find the zeros, okay, of this. So I'm going to find, where this crosses. So basically what's going to happen is that this is going to cross. All right, so somewhere along, okay, so this is your length L, and then this is your area, and it's going to cross. So I'm going to try to find the zeros of this particular relationship. So, well, 1 0 is from the first factor, so that's x is equal to 20. And then the other 0 right here is the second factor, and that's x is equal to 0. So I have my two zeros that happen. So really, what this is, it kind of looks like this. So this really gets shifted, okay, and it's right there. And then those zeros, okay, so what I have, so those points, so this is happening at x is equal to 0, and this is happening at x is equal to 20, right? Now, to find the vertex, finding the line of symmetry there, well, it's very easy in this case, because finding the line of symmetry would have been going across right there, and that is between 0 and 20. So this is going to be just 10. So this point happens, okay, at length of equal to 10. So my L is equal to 10 maximizes my area, which is the peak, okay? So that is the biggest area that I can have for my perimeter. And now, once I have this, I can, of course, just substitute it back into W right here, which I isolated for. But if I substitute L into W, so that's 20 minus 10, which makes W also equal to 10. So what that is telling me, that actually the perimeter, okay, is going to be, so if it's 40, then that means each side is going to be just equal to 10, which actually creates, instead of a rectangle, it's really just a square, and a square is just a special rectangle. And that's how you would be able to solve this. And notice I didn't really have to plot it like I did in the video when I was doing this for grade 9, although I kind of gave you a hint, okay, in terms of drawing it out right here to what to think about. And because it's a quadratic, then this is very simple now to solve. So that's one example, one application of how these quadratics can actually work. And this one is just for maximizing the area. Here's another example that I have for you. And all of these are a little bit different. Again, they'll just, because you haven't seen it, you may not be able to know how to start with these things in the beginning. So this example says Jason, a skydiver, when falling in free fall will accelerate downward at 0.5 g. Now this g, this constant g, you maybe have heard of at some point in elementary school. It is basically approximately 9.8 meters per second squared. It's not exactly, it has more decimal places to it, but we can round it off. Now this constant is just the acceleration that we feel due to the force of gravity pulling us downward towards the earth. So what happens is, so let's say if we're the skydiver right here, okay, what happens is that this force is basically pulling us down. We know that we would be free falling, and we're free falling, now we're free falling downwards. And it says that we're free falling at 0.5 g, and if you do that, 0.5 times 9.8, which is, 4.9, now it is down. Okay, so this is down because it's pulling us downward. So I'll put a negative there, and this is meters per second squared. So meaning that every second we're speeding up at 4.9 meters per second. It's assuming that we're kind of in free fall and we're falling all the way down. Now, technically, at some point, this is going to change, because hopefully we open a parachute, and then it also depends how we're falling. So if this is the case, right, so we're falling at negative 4.9 meters per second squared, so that's what happens. And what we want to know is, now this skydiver jumps from a plane and it is at a height of 600 meters. So basically, so from the start, let's say all the way down to the ground, okay, so this happens at 600 meters. So they're falling down. Now it says, how long would it take Jason to reach a height of 250 meters if he continued to free fall? So let's say if this is 0 meters, because now here we would have hit the ground, which we don't really want to do in free fall. And let's say right here, okay, so this is approximately 250 meters right there. All right, so what happens, and we want to know how long does it take to get to that point. So how do we model this basically as a quadratic? Like how, what do we do? So recall, so let's think about this in terms of quadratics. What do we know about quadratics? All right, so well, quadratics have different forms, right? There's the standard form, y is equal to, so ax squared plus bx plus c. And if you look at this, you'd be like, well, I don't know what the heck is happening here, because these things are falling. It's just 600 meters and then you're going down. Like, what do I do? How do I tie this in? Now, the other equation that we discussed is, of course, there's one which is in factored form, but there's also one which is in vertex form. So it kind of looks like this, where you have a, and then you have x minus h squared, and this is plus k, where your hk was basically your vertex. So now let's think about this falling aspect, right? So, well, when you're falling, you're going to be starting at 600 meters. That's where you're going to start. And then you're going to just fall down. So you're going to be falling down, and that 600 is going to be reducing the distance that you are away from the Earth's surface. So basically, at time t is equal to 0, so at time t is equal to 0. Now, we don't have any times t here, but what I can do is, okay, so my time t, instead of using the letter x, so what I'm going to use is, I'm going to say this is a, okay, let's make x equal to t, all right, and then this is going to be minus, okay, so this is the h squared plus your k. Now your y is basically your distance, okay, so away, so I'm going to put this as d, okay, let's make that distance d, or you can put h for height, but maybe you can put a capital H so it doesn't contradict with this h right here. Now, if we have this, so we have distance is equal to a, and then t minus h, and then k. So again, at time t is equal to 0, we're at a point of 600 meters. So how can I possibly model that, right? So at t is equal to 0. And also, in terms of my starting point, well, where do I start my t, right? My time, really, it's not going to be negative, because you're going to start your time at 0. So we know from the vertex point of view that the value of our time t, or our x, okay, from terms of the vertex, this really is just 0, because that's where we're starting from. And then we're just going to be falling down. All right, so that's what will happen here. So this is going to be d is equal to, so this is now a t squared plus, all right, now my k is, again, because hk is just your vertex, it's your peak of your parabola. Well, we know that we're starting at 0. And then we also know that the height that we're starting at is 600. So our vertex really is just time 0. And our distance is going to be 600. This is t, and then this is our distance. That's our vertex. That's where we're starting from. So this right here is going to be 600, right? So it's 600 meters. And then notice, if you plug in t is equal to 0, okay, then that's going to zero off this term. And indeed, okay, that means at time 0, we are at 600 meters of height. Now, when you're falling down, All right, so we are falling at this speed here, okay, or this acceleration right here. This is what we're falling at. All right, so this is what happens. Notice it's negative. And for that, because we have, so all that's missing is this A, right? So this is the only thing that's missing. We don't know what this is, okay? But in terms of, here is your time t. Now time t is in seconds, because notice you have seconds right there. And then if you square your seconds, right, so t squared. So let's say if it's 1 second, if you square it, it's still going to be 1, but it's going to be second squared because your unit got squared. And what we want is, we want this term to be distance. So the only way to get distance is if you make this A, and that A is actually going to be this A. It is actually how quickly you're falling down, and this is going to be d minus, so equal to negative 4.9, all right, and this is going to be t squared plus 600. And that's your now equation for falling down as you're falling through. And you can check if the units align, right? So notice the units for this, okay, so this is in meters. Now the units for this, okay, so this is going to be meters per second squared, okay, that's coming from here. And then it's being multiplied by t, which is seconds, and you're squaring that. So notice the seconds squared will cancel. And then you just have meters, which is exactly what you wanted for your units. Now, again, when you're in grade 10 and you're looking at these things, these are not very easy and intuitive. But I know that teachers and textbooks and so on, they throw these questions at you. And it's not really until you kind of get into physics point of view, which is a little bit later on, that these things might make more sense. But still give this a try, because I want to kind of see, what would you do if now I would give you this equation, and then I would ask you exactly what it did here. And notice, so it said we're started at 600, and then we want to know how long it took us to get to 250. So what would you do if you had this equation? Well, what you would do is, you would say, okay, well, I want to get to 250, and I know that I have this quadratic right there. So this is a quadratic, right? So this is some kind of parabola. It's pointing downwards. We know exactly what the vertex is. Now, please remember that t is going to be basically greater or equal to 0, right? Because t can't be negative. So this is not a true parabola, because you're going to have a restriction. And then eventually, of course, if you never had a parachute or anything like that, you would just fall straight through. So, there's not going to be a d which is negative, right? You can't just go below the surface of the earth because of the fact, I guess the earth can absorb, right? But unfortunately, if it was a diver, they would pass away due to the injuries if they would just be heading straight down. Okay, so now what do? Well, we have to solve for t. We have to be able to solve now for t. Well, solving for t is basically isolating this thing. So I'm going to move this over to the other side. This is going to be 250 minus 600 is equal to negative 4.9 t squared. Now, 250 minus 600, I guess, is negative 350. That's what you have there. And then dividing both sides. So we're going to divide by negative 4.9, and that's going to cancel this off. So the negatives will cancel. And now you still have this squared. Now to get rid of the square, you can take the square root of both sides. So this comes back to kind of learning, the square roots or roots in general from grade 9. So what is the answer? Well, the answer is, so it's it's the square root of, and now I'll put it in brackets, so 350 divided by 4.9, and that equals, so it's 8, okay, so it's 8.45 and so on and so on. You can round this up, and this is in seconds. Now, of course, because it's square root, so the answer could be both positive or negative, But it can't be negative because time doesn't make sense to have it negative. So it would have been positive. That's how you would have been solving this particular application. And it is a quadratic. So again, if I would graph this out, so let me graph this for you. Let's bring back here decimals. So we have distance is equal to, and this was negative 4.9, let's say t squared. And then this was plus 600. And then don't forget, so in this case, t was greater or equal to 0. And even in this case, so notice, okay, so here's your, let me expand this out, and then contrast it. It's going to go from 600, and then span it out right there. So notice that on here in your y-axis, that's your distance, right? So you're basically just start falling straight down. Now, of course, at this point right here, right, this is 0. You know, you wouldn't have gotten negative. It wouldn't make sense for you to go further than negative. That's what you have. And again, now we wanted basically, so on this graph, you know, you would have gotten to 250. Okay. Now, of course, you could have graphed this out and then just kind of approximated it, but you can solve the equation exactly because you know what the D is and what you want. Okay, so what we will have is an online sales company currently sells 210 books a day. So they're selling books. So notice again a different problem. The cost of each book is $20. After doing some market research, the company notices that if they reduce the cost of a book by 20 cents, so if they're reducing it by 20 cents, then they are capable of selling 25 more books in a day. All right. What discount would yield the highest revenue for the company? So the maximizing sales. So what happens is in here is what they're saying is that you have, okay, so you're selling 210 books every single day. All right, so that's what happens. So you're selling 210 books a day. That's how much you sell. Now, you sell that because you're selling them at $20. Now, what they're saying is, what if they reduce the price? Are they going to increase the number of books that they sell? And typically, sometimes if you do a discount, you might actually sell more. So they said, so here, this is 20 cents. So, okay, at 1980, what would happen is they would sell 25 more books. So this would have went to 200, well, plus 25, this would have went to 235. Okay, if they reduce the price to 1980. Now, if they keep reducing this price, all right, so it means that they're going to be increasing the number of sales. So here it would have went up another 25 per day. So that would have been, I guess, 40. So this is 60 and so on. Now, you eventually don't want to be giving the books for free, right? So the minimum point here is 0, right? Well, if you decrease it all the way to 0, then you're pretty much just giving these books away for free. So you're not making any money. But what you want is you want the highest revenue. So you want to know how far can you reduce this so that it gives you the most amount of revenue. Now, what is it? Okay, so how do we get revenue, right? So how do we make money in terms of, so revenue is just a fancy word in terms of how much money you make, right? How much money you're bringing in. And so here, so what we have is we have the total number of books that you sell, right? So this is the number of books that you sell, multiplied by whatever price that you have. That's your revenue. That's what you are actually doing, right? So it's the number of books times whatever price you have. And we can calculate this. For this, we can multiply these, we can multiply these, and so on. And we can just keep multiplying and then seeing, you know, eventually we're going to, I guess, peak what it's saying. It's going to peak at some point. Now, can I model this in some way? So let's make this revenue, all right? Let's say that this is, okay, so revenue R, and then the number of books. Well, how many books am I selling? Well, the number of books that I'm selling, Well, if I don't do anything, I'll sell 210 books. If I give a discount of basically 20 cents, I'm going to sell 25 more books. So I'm going to sell 25 more books for every discount I give. All right, so let's I don't know, let's call this X. Okay, so this just tells you 210 and then 25 times the discount. So if I give one discount, so one discount will be 20 cents. Two discounts will be 40 cents, right? Three discounts would be 60 cents, and so on. Now this, okay, so this is the number of books that I'm going to sell, and it's going to be multiplying, so it's multiplying the price. Now what is the price? Well, the price is $20. That's the price. But now I'm reducing the price by 20 cents per every single discount I give. So this is what I have. That's what I'm doing. And now, if I multiply these two, now depending on what, so how many discounts do you want to give? 20 cents, 30, 40 cents, 60 cents, how many? 10 discounts, right? Which would be $2. So what will I do? Okay, so this revenue is really dependent on this X, okay? And then so we can call this, Y. So now you can see Y is equal to. Now notice this is in factored form, basically a quadratic. So another quadratic, because if you multiply this through, you can do your distribution, and then you're going to find that it's a quadratic, but you can already see it's a quadratic in factored form. And now, so our goal ultimately, so from here, is what it's asking us is we want to be able to maximize this. And now notice that the sign, so this one is positive, this one is negative. Now the X is second, typically we keep it first. So we would have typically written out as 25X plus 210, and then so on. Now, if you multiply this through, you will notice that, okay, so going back, Y is equal to AX squared plus BX plus C. If you multiply this, you'll notice this A, because one is positive and then this one is negative. So that means this A is going to be negative. Okay, so this is going to be negative. And if it is negative, what does that tell us, okay, about this parabola? Okay, it's going to be looking like this, right? So it's going to look downwards. And again, our Y right here, we want to know what the peak is. We want to know what the maximum revenue is. So what this is telling us that eventually, as we keep giving more and more discounts, eventually our revenues are going to start going down. They're going to peak, they're going to go up, they're going to peak, and then they're going to start coming down. Why are they coming down? Because the price that you give, right, and as you carry through, it might just simply, okay, eventually go to zero, and then you won't have a maximum point. So let's take a look on when that happens. And then we can try to graph it and then see, okay, if we can get that through. Now, because this is already in factored form, so again, what I'm doing is I'm trying to find what this peak is. I'm trying to find really what the vertex is again. So again, let me find the line of symmetry. So I'm going to find where X, okay, in terms of line of symmetry is first. So I can do that by finding out the zeros because it's already in factored form. So from the first zero, so 210, or from the first factor, if I set this to 0, so this is going to go over on the other side, 25x equal to negative 210. So that's what I have there. All right, so this is going to happen, okay, divided by 25. So x is equal to, and so whatever this might be, so 210 and divided by 25, so 8.4. All right, so this is 8.4, and it is negative. Now, of course, we can't have negative, right, because that would mean that we're increasing these prices in some way. So, but for our parabola, okay, so this is this point right here. This happens at negative 8.4. Now, the other zero that we have, so that is 20 minus 0.2x equals to 0. And now, if I bring this over on the other side, That's going to be negative that. Divide by negative 0.2 on both sides. And so here, so the negatives will cancel. All right. So you have just 20 divided by 0.2. So notice that happens at 100. All right. So 100, okay, so that's going to be right there. That's the other 0 that I have. Okay, and that should kind of make sense because 100 times 20 cents is $20. And basically you would have no revenue anymore. All right, so this happens at 100. Now, finding the line of symmetry. So what I have is, so negative 8.4 plus 100. Okay, so negative 8.4 plus 100. So that's going to be, so if I find this line of symmetry from right here, so negative 8.4 plus 100 is going to be 90, I guess 1.6. That's the line of symmetry in there. Okay, we have to now divide this by 2. All right, so that's what we're trying to calculate. Okay, so we have, so 91.6 divided by 2. This happens at 45.8. All right, so that's what we have. That's my X. That's how many discounts I would give. So I would give approximately 46 discounts, right? Between 45 and 46 discounts. And what that means is, so remember each discount, so this is 20 cents. So 20 cents times approximately 46. Okay, so that is my line of symmetry. So what that means, so if I multiply this, so my answer multiplied by 0.2. So this is approximately this much. That's how much of a discount I would have to give. And at that point, the price, which I guess would be $10.84, that would have been the price of the books. This would maximize my sales. So once I have this, I can find what my total revenue is. Okay, so I can substitute it back into the equation and then I can find out what my revenue is. And here they say, what discount would yield the highest revenue? Well, the discount, you would have to discount $9.16. Now, let's plot this so that you can visualize what happens here. So I'm going to plot this out. So 210 plus 25x. This is y is equal to 210 plus 25x. And then the other one was 20 minus 0.2x. All right. And so for this, so I guess it's, so notice that here, let's see how big it will get. And then we'll zoom in here. Okay. So that's what happens right there. And we can stretch this out. And your peak, okay, so right there, 45.8, right? So your revenue is $14,688.20. That's the maximum. And it is a parabola, right? Now, again, so we would kind of restrict x. So x would have to be greater than 0. And also notice that, we don't want revenues which are negative. So, this x, okay, so this 100 right here, this 0, this is basically, that's it. Because here you won't make any more money at all. You're just going to be giving books away. And that's another example and application of quadratics. So you have seen 3. Walk yourself through these. Try to see if you can understand it. And notice that I'm just applying, how do I find a vertex? But when it's just y is equal to, ax squared plus bx plus c, a lot of students are okay. And then when they start having to apply these things to some problems, those are hard. And you probably have seen these now, and you're like, boy, these ones certainly are not easy. All right. Okay, so thanks for watching. And, hopefully some of these examples will give you some kind of a hint where these quadratics can be applied. See you in a future video. Bye, everyone.